This is a picture of how Einstein thought about clocks. So he used photons bouncing between two mirrors to create his clocks. Now, an observer at rest relative to the clock is known as Alice and is shown on the left. Since the clock and Alice are at the same place, the photon just bounces back and forth, whatever the distance d is between the two mirrors. However, Bob is an observer moving to the right. What does Bob moving to the right means? It means when he sees a clock, Alice's clock, the clock moves in the direction opposite to the direction he moves. So we see that for Bob, the clock is moving to the right and the photons are bouncing back and forth as you go along in time. So in order to understand the time beats that are known by Bob relative to Alice, we'll use another picture, and this is the same but shown in a little bit more detail. So Alice's is fixed, and the mirror and the photocell just keep going, flashing back and forth in D. And Bob's looking at the same clock, sees that the pulse emitted moves to the right and is reflected and comes back and received again even further. So because Bob is moving with velocity u, or v is what my equations are going to use. So let's take a look. What happens? Obviously, Alice's clock is pretty straightforward. We have a photon goes up and back. Each distance is 2d. The speed of light is a constant. It's called c. So Alice's clock on the left ticks at 2d divided by c. Whereas Bob's observation of Alice's clock moves on the right and measures a beat using the Pythagorean theorem that the height is still the distance that is going to be let me show it here again. All right. So this is the distance d. This is 1/2 ut, shown there. And we know that whatever time Bob has t, 1/2 ct is the hypotenuse. So 1/2 ct squared is going to be equal to d squared plus 1/2 UT quantity squared. So the distance d, which is the leg, is going to be the hypotenuse c squared t squared. There's a parenthesis around it. Minus v times t squared. The minus is because this is the hypotenuse and these are the two legs. When we now see that t over 2 is on both and they've got a square root, we get t over 2 over here, and we have c squared minus b squared. Okay, so we can take and pull out the c, and we use a term called beta, which is v divided by c. So this is the same equation. Lastly, we divide d by c over 2, and we divide this by c over 2, and then you now have 2d over c. You substitute that into equation 1, and you get t prime is 2ct divided by c2 times gamma, where gamma is 1 over the square root of 1 minus beta squared. And hopefully, from seeing that, you see that it's obvious that the observation of A's clock by B on the right in a moving inertial coordinate system will measure a longer beat than Alice, who's not moving. Going back, we know that Alice's time t prime is gamma times t, which is Bob's measure of time, and in Alice's clock. And gamma, beta is c over v, so it's some fraction of 1. This is 1, this is smaller than 1, the bottom is smaller than 1, so the top is bigger than 1. So this stretches out the time. Bob's measure of Alice's clock stretches the time. It's called time dilatation, and the dictionary calls dilatation the condition of being stretched beyond normal dimensions. So each click that Bob sees in Alice's clock takes longer than what Alice takes. Okay. Once you understand that space and time are unified, then the only difference between that and what we normally see is what we call a pseudo-metric. A metric is how you collect or count up the length of a line or a shortest line length. And in three-dimensional Euclidean or Cartesian metric, that is usually just the length is dx squared plus dy squared plus dz squared. The dx's mean there's a difference between these, and we can actually put them into x's simply by making the differences relative to the origin, and then you have no problems. Anyway, you'll note that all the signs in the Cartesian metric or Euclidean metric are positive. That is, from a mathematician, tells you that it's a Riemannian metric. Minkowski space, which has four dimensions, 1 plus 3, don't have all signs positive. The Minkowski pseudometric has minus c squared dt squared plus dx squared plus dy squared plus dz squared. And the d tau is what we call proper time. And we've used the conversion factor for time of c. So all of this is in the units of meters. All right. Having this, I'm going to again ask, are there any questions?